Let's now continue our discussion about fundamental concepts in mechanics. Another fundamental concept that you should thoroughly understand is Newton's three laws of motion. The first law of motion is for a particle at rest or moving at constant velocity, that they will remain at these conditions as long as there is no unbalanced force. Almost all problem solving that you will soon encounter in this subject revolve around first law of motion. The second law is about the acceleration experienced by a particle when an unbalanced force is present. In physics, we usually take advantage of this law in solving motion problems with the help of the formula force is equal to mass times acceleration. Lastly, the third law simply means that for every action, there is equal and opposite reaction. In the future, we will also keep using of this law, especially when dealing problems related to reaction forces. Part also of laws of mechanics is the Newton's law of gravitational attraction. This law is simply about the attraction of two particles and is expressed as follows, in where the force of gravitation between two particles is simply equal to the universal constant times the product of the masses of the given two particles all over the square of their distance. This law is very essential in arriving to the value of acceleration due to gravity. Take note that 9.81 meter per second squared and 32.2 feet per second squared are the values that we will keep using for acceleration due to gravity. Now that the laws of mechanics were presented, let's see now this common application, which is the concept of force. As defined here, force represents the action of one body on another, or in physics, it is a push or pull upon an object due to objects' interaction with one another. Take note that it has three characteristics, namely point of application, magnitude, and direction. First is the point of application. As you can see here, the force, which is 50 Newton, acts on the box, specifically on point O. Thus, point O is the point of application. Second is the magnitude, and in this figure, it is this one which is force expressed as or is equal to 50 Newton. So that defines the magnitude of the force. And lastly, direction of the force, which is described by the line of action and arrowhead. So the line of action is this dashed line, and this is the arrowhead of the force. Take note that the direction of a force is also defined by an angle. In this figure, it is this 30 degrees angle. Also, direction is defined by this dashed line called line of action. So line of action is this infinite straight line along which the force acts. In SI units or international system, force is expressed in newtons. Previously, we see that 1 newton is equal to 1 kilogram multiplied by 1 meter and divided by a square of a second. In US, or also called as, or also termed in the other references as English units, first is a force is expressed as pound force. Remember that the unit of mass for this system is expressed in slugs. This time, let's discuss a very important principle that you can utilize when solving problems involving several forces, which is the principle of transmissibility. It states that the external effect of a force on a body is the same for all points of application along its line of action. This means that when analyzing mechanics problems, you may draw the forces to be not in contact with the point of application as long as it is still acting on the same line of action. This animation is an example of applying this principle. As you can observe in the animation, you may transmit the force in your analysis from one point to the other point as long as it lies on the same line of action. Though the nature changes, as shown from push to pull, the external effect remains unchanged due to the principle of transmissibility. In both cases, the object tends to move to the right. With the knowledge about the concept of force and this principle, we can now extend to situations in where multiple forces are involved. The setup of several forces acting on a body is called force system, and these are some of the situations of how force systems look like during analysis. So later on our advanced topics, we'll be dealing with force systems and also their equilibrium. So for now, this is just for visual purposes on how force system look like during analysis. A force system can be classified as shown in this diagram. Again, this another classification might be somehow overwhelming, but let's go through them one by starting first with the two main classifications of force system, the coplanar and non-coplanar. One of the main classifications of force system is coplanar force system. From the word coplanar, it means on the same plane. As you can see on its figure, forces indicated by F sub 1, F sub 2, and F sub 3 are acting on the same plane. Thus, they are coplanar forces or they form a coplanar force system. At the same time, it is indicated here that the forces are concurrent. Later, we will deal with this subclassification. But for the moment, let's proceed with the next one, which is non-coplanar force system. This system is just the opposite of coplanar force system. As shown here in the figure, this group of forces do not have a common plane where they act. Thus, these three forces as a whole formed a non-coplanar force system. With these two main classifications, let's proceed with their subclassifications. Whether a group of forces is coplanar or non-coplanar, they can be further classified into three sub-classifications. One of these is first the concurrent force system. This system simply means that the lines of action of the forces intersect at a common point, as shown here in the figure, in where point O is the common point of all the line of action of the given forces. So it is just the same in mathematics in where concurrent lines are those lines that meet a single point. Next subclassification is parallel force systems, in where regardless of the sense depicted by the arrowhead, the lines of action of the group of forces are parallel. In this figure, the set of forces acting on a plane parallel to your screen are first classified as coplanar, only for these three forces, and then subclassified as parallel force system. Additionally, the parallel force system is further divided into like and unlike parallel. In this case, although they are parallel, their directions are not all the same, as indicated by their arrowheads. Thus, as a group, they are considered as coplanar, unlike parallel force system. On the other plane, at the top, they are acting on one plane. So they are acting on one plane, they are parallel, and all pointing at the same direction. Therefore, they are considered as coplanar, like parallel force system. This one is an example in where even the forces are acting on different planes. They are, they are all still parallel with each other. Note that these four forces are pointing on the same direction. Therefore, for this group of four forces, they are classified as non-coplanar, unlike parallel force system. So let's proceed with another subclassification, which is the general force system, in where the forces are neither concurrent nor parallel. So this means they cannot be further classified by these first two subclassifications. These first two subclassifications. These are the examples on how it looks like. These two system of forces can be classified as either coplanar or non-coplanar, but they are both non-concurrent and non-parallel. And you can observe from here that they can, for example, this figure they cannot be concurrent for system. Even you extend the line of action, they will not have a single common point of intersection, and they're not also parallel. And the same goes with this figure. Take note that coplanar force system, only for coplanar force system has one more sub-classification, which is collinear force system, in where the line of action of the forces are coincidental, or in other words, all the forces share a common line of action. This is usually seen on ideal members of steel trusses or compressive members of a machine. So this is one example. They share a common line of action. Although now that you have an idea about the concept of a force and the force systems, it is still necessary to have some kind of solid reference to conduct mechanics analysis on rigid bodies. This reference is called Axioms of Mechanics, which are self-evident facts. Although they cannot be proven mathematically, but they can be demonstrated to be true. These axioms will serve as a fundamental reference in studying mechanics and can later on, in our advanced topics, enable you to analyze equilibrium more quickly. So first is about parallelogram law, which we will focus later on this lecture. Next is about two force members. This figure from the previous slide is an example of a two force member, which means that for a member or body, two forces are in equilibrium only when equal in magnitude, opposite in direction, and collinear in action. For this figure, since the two forces are already collinear and oppositely directed, the body can be said to be a two-force member as long as the magnitude of force F sub B is equal to magnitude of force F sub D. So that is the concept of two force members. The third axiom is about adding new set of forces. When an existing system of forces is already in equilibrium, let's say this one, it is still possible to add a new set of forces which will not alter the effect produced by the original system of forces. If in this figure, let's say we add uh, two new forces, if in this figure these two added forces are equal in magnitude, collinear and oppositely directed, this new set of forces will not affect the equilibrium of this body. So this is the third axiom of mechanics. Lastly, we have Newton's third law of motion, which we have discussed previously, in where for every action there is an equal and opposite reaction. To deal with computations involving force, which is a vector quantity, we need to review the vector operations which we have already, as a student, we have encountered during our physics class. So for vector operations, let's discuss first the easiest, which is multiplication and division of a vector by a scalar. For these operations, they are similar with multiplying and dividing two scalar quantities. However, in these operations, the sign of the scalar quantity affects the direction of the vector. For example, you have force vector P and you multiply it with positive 2, which is a scalar quantity. The answer is simply twice the force vector P with positive direction. Another example is you have force vector Q and you divide it with negative 2. The answer is simply half of the vector Q with negative direction. The next operation that we will review is vector addition, and can be performed in three ways or three methods: by parallelogram law, triangle rule or triangle law, and lastly by rectangular component method or by component method. In this lecture, we will go through first with the first two methods of adding vectors. We will cover the component method on our next lecture when we discuss force resolution. So first, vectors can be added using parallelogram law. The result of combining the force vectors is called resultant force. As defined here, it is a single force that can replace several forces which produces the same effect on a particle or body. With parallelogram law, we can solve for the resultant by getting the diagonal of the parallelogram formed by the vectors of the given forces. For example, you have a particle acted by two vector forces q and p and with a given angle of inclination. To solve using this method, all the given forces must be connected tail to tail as shown here. To draw the resultant, you need to draw first the projected lines parallel with the given forces and connect them with the arrowheads of the given forces to enclose a parallelogram shape. The length of each force vectors represents their magnitude. From here, you can draw the diagonal, which is the resultant force in this method. So you will just connect it with the tails of the given forces and the other end of the lines of the dashed lines. The length of the diagonal represents the magnitude of the resultant, while its angle of inclination describes its direction. By applying trigonometry, we will be able to get the necessary dimensions so that we will be able to use the cosine law to get the resultant, to get the magnitude of the resultant. Take note that since we want to get the magnitude of the resultant, we need to find first its opposite angle. That's why we need to apply first the trigonometry in our illustration or drawing. While for the inclination, represented by angle B, cosine law can also be used. In this case, we just have to simplify the equation and solve for angle B. So that's the procedure for this method. Next method of adding vectors is by triangle rule or triangle law, which is just a special case of parallelogram law. However, the procedure of solving the resultant by triangle rule or triangle law has some difference from parallelogram law. To perform this method in solving for the resultant force, let's consider this example. A particle acted by two given inclined forces Q and P with given angle of their inclination, angle A and angle B. The first step is connect two or more vectors from head to tail, such as this one. The force vector P is connected to force vector Q by a head to tail connection. The next step is locate the resultant or draw the resultant by starting from the tail of the first drawn vector and connecting the head of the resultant to the head of the last drawn vector. With the resultant drawn in the figure, you can now solve the required magnitudes or directions by using trigonometry. So again, for this lecture, we will skip with the third method, which is the component method. So in the next topic, we will go through with it as we learn about force resolution. For now, let's discuss about another vector operation, which is vector subtraction. For vector subtraction, all the three methods of vector addition, as outlined previously, are also applicable. However, we just need to include one more step in our solution, and that is to consider the effect of the sign of the vectors. For example, we are tasked to get the resultant of the difference between two force vectors P and Q. Then we can simply write resultant R is equal to force vector P minus force vector Q, and then modify it a little to draw the illustration later much easier by expressing resultant R equal to force vector P plus negative of force vector Q. To visualize, let's consider drawing first positive a drawing of a positive force vector P and a positive force vector Q acting on a particle. Since we want to get the resultant of the difference, we have to redraw the figure as follows. It can be noticed from here that a negative of force vector q still have the same magnitude as represented by the length of the arrow line. Also it is still along the same line of action represented by this dashed line. However, it is now directed in the opposite direction. Therefore, when dealing with vector subtraction, you just attach the negative sign to a vector. That's what we did with force vector q. Then use the same magnitude and line of action. And finally, just change the direction into its opposite. So this vector, the direction of this vector is just the opposite of the direction of this vector. With that procedure, we can redraw the figure like this one and then apply one of the methods from vector addition. So that's it for now. Kindly refer to the last part of this lecture in where we will solve some sample problems. So thank you, class.